Hello and welcome. In this video, we'll be covering section 7.3, which is over proving trigonometric identities. My goal for you by the end of the video is to be able to prove some identities utilizing other trig identities, as well as to be able to use the product to sum or sum to product identities as a way to either simplify or derive other identities. So majority of this will be similar to the simplify, but this time it will actually give you like an end goal that you want it to turn into. So hopefully this will seem a little better, but it still is a little bit more abstract type of thinking. So first off, let's talk about approaches to doing these. So all of these are just more like guidelines or hints, or even just nudges in the right direction, whatever you might want to call them, but these are all the exact same as what you will find in the notes. So I know it's pretty wordy, so probably is pretty small on the screen, but essentially what we're trying to do with the proving identities is picking one side of an equal sign. So they're going to give us some expression that apparently is true, and to prove it, I just pick whichever side seems like it would be easier to start with and try and manipulate it until it simplifies into whatever the other side happens to be. So usually a good rule of thumb is to start with whatever looks more difficult or seems to be a little bit more complex in appearance, and try and manipulate and simplify, because it's usually easier to simplify than it is to try and make something that actually is super simple to start turn into something that's maybe more complex. So just kind of thinking of as far as an approach to go with, don't necessarily always choose the left side or always choose the right side. Just take a quick glance, look at each, and if one looks like it's worse than the other, maybe start trying without one. Now if you feel like you get to a point where you don't know what to do, then at that point maybe stop and start over. Don't necessarily erase everything, but maybe try starting with the other side and see if somehow, some way, maybe you might meet in the middle. And all of this hopefully will make sense by the end of whatever examples I end up working through here. But as always, if you have other examples that we want, we can work through a few more in class as needed. But as far as some other approaches, other than just working with the most complex side, sometimes it would be beneficial to try like factoring or maybe multiplying out a pair of parentheses, kind of one way or the other. Or sometimes if there's some like terms that you can maybe add or subtract with one another, by all means start with doing that. If you end up ever having rational expressions, meaning there's some fractions involved, sometimes creative use of multiplying by 1 can be helpful. So such as like making a common denominator, so maybe I can make two fractions turn into 1, or sometimes a conjugate pair may take something that's not a Pythagorean identity but turn it into a Pythagorean identity. So there's again some creativity and again having to think outside the box that may be necessary with these, but as you practice it more and more and more, the ideas of what you could potentially do next and kind of think ahead and go, if I do this, here's what will be that chain effect, should in theory happen as you do more and more of these. Another thing that can be useful is, since every single function can be turned into sines and cosines, sometimes if you're completely stuck, that's a good start as well, just so you only have to worry about those two functions and whatever identities they maybe could turn into. But it also gives you the ability to kind of narrow your focus a little bit and only have to worry about those two. And again, the very last one's my favorite one. Just at least try something. Pick a side, go, see what happens, try plugging things in. Ultimately, if you start getting things to start going into at least some direction, oftentimes it may open up something that you now recognize in a step or two after you just manipulate, and then maybe it kind of has the light bulb turn on and then you kind of see where the problem goes. But again, like I said, I don't expect anyone really to be perfect with this at first. It's something that you just have to kind of grind through, try things out, just pay attention to what the cause and effects are each time you do some of these substitutions, and then don't just delete that from your memory banks. Try and store that in there, and next time you see that specific thing, hopefully you can remember like when you did something specific, it turned into something that you wanted it to, and maybe try following that approach because you knew it worked in the past. But that's, again, there's general guidelines for this. It's not really a step-by-step, always do this first or this second or this third. It's more, again, just ways to think about approaching a problem, and hopefully that at least gives you a nudge in a direction that you can maybe follow. All right, so we'll go ahead and jump into the first example. If I didn't say so already, it might be beneficial to have a reference page with a fair amount of these identities, just so you can easily find or identify maybe whatever substitution I might do. But again, the more comfortable you are with the identities and what they can and can't turn into, the easier or maybe faster it is to kind of think through some options as we work through them. So each time, again, as far as an approach, the best thing to do is just pick a side and start with whatever you think you might be able to do. So with this one, I see that I've got just two terms without a power, and then I see on the other side I have two terms that do have a power. So if I had to personally make a decision, I would probably go after the side that has a power, because I can think of some options that I already have, which would be just expanding out that power and seeing what it turns into. So that's where I'm going to begin with this problem. So I've kind of set my goal as I want to turn the right side into this 1 plus sine of 2 theta. So we can also start thinking of maybe some of the things that the left side could turn into. Sine of 2 theta is a double angle formula, so if I see that there's maybe something that resembles that pops up, I might have the ability to replace it. But anyway, if I go ahead and expand out the right side just to get rid of the power, expand the power to get rid of the parentheses, I'd end up with a sine times a sine, so for sure it would start with sine squared of theta. Looks like my middle terms would just be these two again multiplied repeatedly, so that's going to give me 2 of those sine of theta cosine of thetas. If it helps, you could also organize your thoughts with this one using a Punnett square if you're comfortable or more comfortable using that. And then the last one would be a cosine times another cosine that will give me a cosine squared of theta. And so at this point, hopefully we start recognizing some things that we could do. Sine squared and cosine squared, those two things, when not multiplying, but add them together, that actually is one of the Pythagorean identities. That turns into a value of 1. Then I have on the other side of this, or the other part that I haven't used is this part, so it's just going to kind of tag along for the time being. But you might have even been able to recognize that that actually is an identity as well. This is a double angle formula for sine. So those two terms with a 2 as a coefficient in front will actually turn into sine of twice whatever that angle was. In this case, it was theta. And wouldn't you know it, what we just got matches what the other side was. So technically we've checked that box and we've proven that the right side with just manipulations can turn into the left side. Hence this ability, or the identity that was presented was actually a true statement. The left side did in fact equal the right side. So as far as like kind of a key takeaway with this, what is the actual answer? Well, it kind of gave us the answer, but the actual answer is all of the work here in the middle. So this part right here is actually where all of the points, if I were to kind of explain how the grading would go, is that's where all of the actual points would be I guess assessed, if you will. So the answers for these is actually the work, not so much the end result. We just know what the end result should be. I just have to find a way to connect the dots with whatever I'm starting with and whatever it's supposed to finish at. So let's go ahead and try another example here. Example 2 wants us to try and prove this identity as far as some options that we potentially could see. We've got some tangents that are multiplying with the sine, or we have some tangents multiplied together that are subtracting with the sine. So as far as this one is concerned, it kind of seems like it's a flip of the coin which side is going to be tougher to go with. So I'm just going to follow that 5th piece of advice. Just pick a side and try it out, see where it goes. If it doesn't seem to go very far, then I'll maybe switch my mindset, try starting with the other side and just see where that goes and find a way to maybe hopefully connect somewhere in the middle. So I feel like the left side reading a product is probably going to be a little bit easier to deal with, but to each their own. We could maybe try dealing with the other side as well. But let's just, see what's going to happen. So if I think about what my options are here, again, one of the other strategies is let's just switch everything to maybe sines and cosines. So I could say the sine squared of x is over a 1, and then switch the tangent squared of x to maybe sine squared of x over cosine squared of x. And that kind of gives me an idea of, instead of putting that over a 1, maybe thinking about how can I take that sine squared of theta and change it to something that maybe would multiply and cancel with that cosine squared of theta. So my first instinct here is to take this guy and utilize one of the versions of the Pythagorean identity and turn that into 1 minus cosine squared of x, or the tangent square that was outside, which really was the sine squared of x over cosine squared of x that we created just a second ago, stays outside. But now I've created something that now actually has subtraction. So if we kind of look at our end goal, we are trying to make subtraction. I've successfully done that, right? I've created something that now has that minus in between two terms. I just don't have parentheses, so that would be now, because I created the parentheses, the next thing I would try and go after is how do I make them go away? Now that I've replaced something with two terms, I need to probably distribute through whatever was on the outside. So if I do that, this first term would now be sine squared of x over cosine squared of x. And then the second one, kind of the whole point of me switching out of sine squared and turning into cosine squared is so when I distribute this through, the cosine squared of x divided by cosine squared of x actually just leaves whatever the numerator is, which is sine squared of x. And at this point, we can hopefully see that we could switch the sine squared of x over cosine squared of x back to now tangent squared of x. I have my minus sine squared of x after that, and voila, that's exactly what we were trying to create. So technically I was able to show that each one of these was able to finally come back full circle and turn into the other side. So I can check that box that yes, I satisfied this specific identity and proved that the left side could in fact turn into the right side. Now, is this the only actual solution to this? Absolutely not. There actually are multiple ways for you to solve these. That sometimes it could be done in maybe 1 or 2 steps. Sometimes it might take 5 or 6 or 7 or 8 steps. It just kind of comes down to how you see it, what you try as your first step, and how you want to manipulate. Honestly, we could have actually started with the right side and figured out a way to turn it into the left side as well, and it actually would have been the exact reverse of the steps that I just did. So if you wanted to maybe try that out on your own, maybe try starting with the right side, and just by doing almost the exact reverse substitutions that I did here, maybe see if you can turn it into the left side or make it turn into a product. Moving on to yet another example. So pretty much the whole video here, if you haven't been able to kind of tell, like, it really is just going to be, let's just see as many things of how to approach these as possible, and hopefully each time you kind of gauge, like, okay, when this happened, this is what he did, or this is what I should maybe try doing, and just kind of, again, learn from experience more than anything else. It's legitimately something where the more you practice it, the easier it is to see the avenues. At first, it just seems like you're kind of pulling stuff out of thin air, which is okay, at least as long as you're trying to substitute things in certain spots. You hopefully can eventually start seeing some of the patterns that develop, and then have a little bit less guesswork going in as you maybe do your 5th or 6th or 7th or 8th example in your own assignment or just your own practice. So anyway, if I go ahead and continue on, this specific example here, it looks to me like I can turn into sines and cosines a lot easier than it would be to turn into cotangents and cosecants. So I feel like the smart side to start with would be this left side. So that kind of gives me an idea of I'm trying to make something that's 2 terms turn into just a single fraction. So I feel like probably common denominator type idea is going to get involved somehow, some way in my future. So I'm going to go ahead and just replace each of those in terms of sine and cosine, since that's going to be my goal anyway. So cotangent, if we think about it, should turn into a cosine of x over sine of x. The other option would have been to make it turn into 1 over tangent of x, but looking ahead, I don't see any tangents on the right side, so getting out of the tangent and cotangent kind of connection I think makes the most sense. Then I can try the next thing, which is replace cosecant in terms of its version in sines or cosines. Cosecant of x happens to match the 1 over sine of x, so I've at least now got sines and cosines, and we'll kind of see what happens from here. Now, what actually was kind of nice about those substitutions is these already have the common denominator that I kind of mentioned before. So if we think in terms of like what will that get to turn into, well, this should be able to turn into one single fraction, where I've got cosine of x plus 1 all over a sine of x. So I can make those 2 fractions turn into just 1 fraction. So I'm getting closer to the appearance of what the right side is. It still just doesn't match quite yet. The other thing that seems a little bit off is the cosine is after a 1, whereas right now I have it in front of the 1. So one option we could technically have done is we also could have just switched the order, since after all it is addition. And I think I'm actually going to go ahead and do that just to show maybe a little bit nicer the next step, or at least make some sort of logic behind whatever the next step is. And at this point, I would go ahead and think in terms of how could I make whatever it has in the end actually happen. So this is where a conjugate pair could happen. We could look at what we need. We need to have a 1 minus cosine of x on the bottom. So what we could do is just force that hand and just say, let's multiply the bottom by 1 minus cosine of x. I just would then have to multiply the top by the same thing. So this is where kind of taking advantage of, like, I know what the end result is. I know it needs to have that, so maybe let's force it. But again, this is like that from the suggestions earlier, just a creative way of multiplying a fraction by 1. It just happens to be a pretty smart chosen one because it actually is a conjugate of what's on the top, and it also is where I'm trying to get a 1 minus cosine in the end. Now if I go ahead and multiply out the top, because that's a conjugate pair, it should just square both terms and keep subtraction in between. So 1 squared is 1, cosine squared after the minus, because I do technically have the middle terms cancel, a positive cosine with a negative cosine, and then a negative cosine times a positive cosine does give me the negative cosine squared if you needed me to connect the dots there. That just happens to turn into something that eventually I'll be able to replace, but I'm going to go ahead and just rewrite it because having sine of x in front of a parenthesis seems like a better place for it, but I could have left it in the same order. That's more of just a personal preference than anything else. So I kind of ran myself out of room vertically, so I'm going to go ahead and just kind of connect the dots here and show what this will turn into next by drawing the arrow. This is now going to turn into, if you look on the numerator, 1 minus cosine squared of x is a Pythagorean identity. That actually would be able to be replaced with sine squared of x. And that still would be over, and it was intentional. I forgot to mention the y, but I think I mentioned when we were doing this simplifying, at least in class, that you usually try and keep denominators factored as long as possible, or just hold off on multiplying out, because ultimately what we're going to try and have happen is the stuff that's outside of parentheses potentially, or maybe even full parentheses alone. We're trying to get them to potentially have something to cancel with in the numerator. At this point, I think we maybe should all see that there's a sine of x on the bottom that can cancel one of the sine of x's on top. And now look at what we got. That's now created a sine of x on top of a 1 minus cosine of x on the bottom. And voila, that actually was exactly what we wanted. So we've checked the box. We proved just by manipulations that the left side could in fact equal the right side. Had I wanted to start with the right side for whatever reason and thought of maybe finding a way to split up whatever that fraction was into two terms, would have been a little tougher, I think, because it would have been a little bit more thinking outside the box than what we had to do here, but it would have been kind of the exact reverse, either multiply top and bottom by sine, or I could have maybe multiplied top and bottom by the conjugate of 1 minus cosine of x, just so eventually it would turn into a 1 minus cosine squared of x that could then turn into a sine, and then maybe I would be able to split it up into two fractions because I made the bottom turn into one term. But again, it doesn't really matter which side you start with. It really is just a matter of which side do you think has the best first step, or at least has something that you have an idea of trying, and just give it a whirl, see where it takes you. And if you get stuck, like I said in other or earlier in the video, just maybe start again. Don't erase what you have, but see if you maybe start with the other side, that somehow maybe you could connect in the middle. So like maybe we would connect here at the bottom of what I have there if I maybe started with this and worked my way backwards. But again, that's just a way that you can kind of see if you are completely stuck. A way to maybe get yourself unstuck is to just try it from both sides and see if somehow, some way you find a common place somewhere in the middle of your work. Move on to yet another example. Again, the more you see, hopefully the easier it is to identify some patterns and some strategies to try. For this one, at first glance, it seems to me like the right side is definitely more complex than the left side. I feel like the left side is actually the simplified version, so I'm going to go ahead and just choose the right side and just see what I can manipulate to turn into. Again, my end goal here is now I want it to turn into somehow a secant of 2 theta, which I really, if I kind of think ahead, that might just turn into a 1 over cosine of 2 theta, because I actually have a formula for cosine of 2 theta. So I'm kind of thinking that will probably happen at some point near the end of my step, so that last step would turn it back into a secant. So that's kind of what I'm thinking ahead about. Now, as far as what are some options that I could do initially with this one, I feel like switching out of secants might be a smart idea for a little bit, just to see what might happen. So if I did that, this would just turn into a 1 over cosine squared of theta over a 2 minus a 1 over cosine squared of theta. So that first step actually seemed like I made it kind of worse, but again, I'm a little bit more comfortable, or I feel like there's more options when you have sines and cosines. So that was kind of my initial line of reasoning, even though it did kind of make it worse. I made fractions now inside of a big fraction. Now, if we think of some of the strategies we've had when that has happened, is we've been able to just multiply the top and bottom by whatever denominator we just saw, or whatever the common denominator would be. So in this scenario, I feel like to cancel the cosine squareds that are in denominators, I could just distribute through a cosine squared of theta on top and bottom, and just see where that takes me. So if I do cosine squared of theta times 1 over cosine squared of theta, the top actually turns into 1 pretty quick. The bottom I would have to distribute to both, so the 2 has to get multiplied by that cosine squared of theta. Whereas the cosine squared of theta times the 1 over cosine squared of theta, just like it did in the numerator, is going to turn into a 1, but it still had the minus sign, so I'm going to keep it as a negative 1, technically. From here, we can maybe recognize that that bottom actually is one of the cosine double angle formula versions. So I could technically replace that with cosine of 2 of those thetas, or twice theta. And at that point, I hope we recognize that 1 over cosine is the same as doing secant. So I can move that to the numerator and call it secant of 2 theta, where the angle is just staying the same, and wouldn't you know it, that is exactly what we wanted it to turn into. So once again, we connected the right side this time to the left side just by manipulating and utilizing some other identities. Moving on to yet another example. With this one, again, first glance, it's just always a pick a side to start with, see what happens. I feel like the left side this time is definitely going to be the side that will give me some options, whereas the right side, just making secant turn into all of that stuff, seems like that would be really a lot of pulling things out of thin air, just trying randomness. So again, the left side gives us more things that we can at least try and replace. So that's where I would start, at least focusing my attention. So as far as what can I do with that, the first thing I kind of notice is the fact that I've got 2 x's that are intermixing with things that have 1 x's. And if my end goal is to just have an angle of 1x, I feel like I probably should try and get those 2 x's out of there as quick as possible. So I do happen to have a couple of formulas for each of those. The double angle formula for sine of 2x just turns into 2 sine of x cosine of x. And that would be still over the sine of x that was in the original denominator. So if we kind of foreshadow what that's going to allow us to do, it looks like the sine of x on top and bottom will actually cancel each other out, so that's kind of nice. And then the cosine of 2x, I do have to keep that minus sign, be careful with that, but I'm going to replace the cosine of x with its value, and it's actually got 3 different options. So let's see if we can maybe think ahead and go, what makes the most sense? So if the sines are going to cancel with this one, I feel like I probably want to try and choose some version that has only cosines, because I'll only have cosines left if I look at everything else that's there. So I'm going to choose to go with the 2 cosine squared of x minus 1 version of that double angle for cosine. But again, I technically had 2 other options I could go with. I could have just picked any of them, tried it out. It's just I'm kind of thinking ahead going, well, the bottom has a cosine of x. If I could find a way to maybe cancel that, that might actually be kind of nice. So from here, as we already probably foreshadowed, the sine of x on the first one does cancel, so it does in fact leave me just 2 cosine of x. And then I do have to make sure that this minus distributes through. Just kind of keep that in mind when it goes through, because it is in front of the whole fraction, not just the first term of the fraction. And I think I'm going to go ahead and split this into 2 fractions, just to kind of at least get things to start separating to where maybe I can combine some like terms in the next step. So if I did that, this would turn into 2 cosine squared of x over the cosine of x. And then I've got the double negative on the 1 at the end here that will turn that into plus 1 over a cosine of x. And you probably already saw or thought of what was going to happen next, but again, the whole point of me splitting that up is so now potentially that cosine on the bottom was able to cancel with something. Well, there's a couple of them on top, so at least one of them would cancel, but the coefficient of 2 is staying there. So notice at this point I've got 2 cosine of x minus, that's actually turned into 2 cosine of x as well, so those actually are going to zero out. And we may as well go ahead and look at what 1 over cosine of x could turn into. Well, that would just turn into a secant of x, or I could rewrite that as secant of x. And as mentioned just a second ago, these two do in fact add up to equal 0. So instead of me putting 0, this all together is just going to turn into secant of x. And once you know it, that actually is exactly what we wanted. So it goes around full circle again. So again, check that box. Those two actually did turn into, I'm going to go ahead and just maybe for video purposes, that was 0. But again, that checked out that secant of x is all that was left. That matched what I was trying to turn it into, so I've now technically proven that the left side could turn into and match the right side. Alright, so the second main concept of this lesson is the other part mentioned at the very beginning, the product to sum or sum to product identities. And ultimately this is just a way for us to manipulate one thing that's a product into a sum or sum to product, hence the name of these particular things. As far as the why we would care to do it, again, that's more of a future class where having this skill set kind of shows itself as to why maybe I would want a product to turn into a sum or vice versa. But for interest of right now, just think of it more as like I'm just continuing to practice the idea of manipulating something, utilizing a formula or an identity as these are called, and then turning it into something else. As far as the application is concerned, that again is a little bit above or a little bit in our future. So kind of just think of this as we're just building a skill set that eventually later on you hopefully will see an application for. Potentially, I guess I could show some examples of this in class. I don't know how much they would make sense, but there is a time and place where it makes sense to do both of these directions. So again, this is just more, can we follow a pattern or can we plug numbers into the correct place and simplify? And this is actually where the even and odd identities will on occasion pop up as well. So this is where maybe a small application, I know I said it was a rare thing for those to get used, but this is one of those places where that rare usage does happen. So just as a quick reminder, anytime you have a negative inside of a cosine function, you can technically just drop the negative inside. For sine functions, you can drop the negative but make the whole function negative, so it's almost kind of like you're moving a negative out in front of that specific trig term. And if you notice what we have here, it's just only sines and cosines that we have to worry about. So really, if I can just remember those two even and odd identities just for those two functions, it may pop up from time to time when it comes to working through these problems. But I just have a couple more examples with this, so it shouldn't be too much longer in this video. So without further ado, let's go ahead and jump into one. Alright, well, this example, as you can see, wants us to just find an identity for this. So you could really think of this as it just wants you to simplify. It wants you to kind of show what it could turn into. So if we kind of break down what we got, we've got two cosines being added together. So this is starting as a sum. So if we think about what we had just on that previous slide, that means I should be able to potentially turn it into a product using one of those identities. So if I go ahead and show what that would be, here the formula that we have, if I go ahead and maybe write just the basics of it, the cosine of A plus the cosine of B, that formula was supposed to be able to turn into, if we had one nearby, it turns into 2 times cosine of the two angles added together over a 2 times a cosine of the two angles, this time subtracted, and divided by 2. So again, that would just be a reference on unit circle. I didn't use my space very well right there, but the idea of I'm just going to plug into that formula. As you can see in this case, I kind of know that my A is just going to be a theta, and my B for that formula is going to be a 5 theta. So if I go ahead and just plug into this formula that I just created, I know it's going to start with the 2 in front. The cosine, first one, it's supposed to add those two together, so that would be theta plus 5 theta over 2. And then times cosine of, this time it's going to be theta minus 5 theta over 2. And just thinking ahead, I probably will be able to just add those together and divide by 2. So this first one, it looks like I've got 2 cosine of 1 theta plus 5 theta is 6 theta. If I divide that by 2, that gives me 3 theta. And then the second one here, it looks like I get cosine of theta take away 5 theta would be negative 4 theta. And negative 4 cut in half or divided by 2 would be a negative 2 theta. And as I mentioned not too long ago in the video here, cosine is the even function, so this negative that I've created right here, technically I can go ahead and utilize the fact that that's an even function and just drop it for my final answer and just call this 2 cosine of 3 theta times cosine of 2 theta. I'll go ahead and throw some parentheses just to stay consistent with everything else that I've been doing on that problem. And there we go. We've got that this identity apparently would be able to turn into this expression down here on the bottom. And ultimately from here I could continue trying to manipulate. I could turn that into secants potentially. I can't really multiply those two together because again a 3 theta and a 2 theta are different angles, so I couldn't make that turn into like a cosine squared at all. It does have to match perfectly inside for that product to happen. But yeah, this is just our first example, or one example, of doing a sum and turning it into a product just by utilizing the identity that was provided or is on our formula sheet. So I'm sure you could probably foreshadow what we were going to do next, but if that one was a sum that I turned into a product, again, that's just one of 4 possible ways that that could be provided, but as far as the approach, it would be the same even if it was a pair of sines added or a pair of sines subtracted or a pair of cosines subtracted for that matter, right? We just have a specific formula to follow, so I would just make sure I put the A's and B's in the right spots and just kind of simplify as I go. So if I did a sum to product, as I kind of just assumed you probably figured out, we're going to now do a product to sum. So initial here, I just kind of look at what do I have. It does have the 2 in front, but sometimes you have to get maybe potentially a little creative with where that 2 might go. But if I look at what I have here, I do have a 2 that's in front. I'm going to go ahead and just kind of separate that for the time being. And then I do have the product in the inside. So if we look at our sum to product ideas, this one has sine multiplying with cosine. So the formula from our sheet that I'll end up using is the one that goes, I'll give myself a little more space this time, and be the sine of A times cosine of B is equivalent to the 1/2 large bracket or large grouping, and then the first one is sine of the 2 angles added together, A plus B, and then the other one is plus sine of the 2 angles subtracted, specifically in the order A minus B. So it looks like to me my A's in this case are the 3 thetas and my B's in this case are the 7 thetas. And now I just follow the formula. So if I go ahead and replace the part here with what I have, so notice again I've kind of separated that 2 and just moved it out front. And so now if I replace it, I've got the 1/2 that's going to go first right here. Then it's the big grouping here, sine of A plus B, so that's going to be sine of, just to show all of the work, 3 theta plus 7 theta. And then added with sine of the 2 angles, this time subtracted, so 3 theta minus 7 theta. And again, that was all grouped up, and I'm going to go ahead and just say, okay, let's close off the other grouping I had at the very beginning, and now it's just a matter of what do I need to do? Well, the 2 and the 1/2 here in the front actually are going to just turn into a 1, so I can go ahead and just say those two actually cancel each other out. And now simplify what's inside, so it looks like I've got sine of 10 theta, and then added with sine of 3 take away 7, that would give me down to negative 4 theta. But again, sine is an odd function, so just like before, that negative sign that popped up here, I just need to take advantage of what that means in an odd function. Well, ultimately what that thing is going to do is it's going to look like, or kind of appear like it's just going to bounce itself out front. So that plus sign that there is actually going to turn into a minus sign. So I've got sine of 10 theta still being the first term, but then minus the sign of now, because I've dealt with that negative, now it's a positive 4 theta. And voila, I've been able to turn what was a product now into a sum of 2 angles. And again, there's certain times and places where this would make sense, why I would care to make a product turn into a sum, or vice versa. But again, that's more of a future us or future class where you would actually see like the benefits of why right now, or why at that point. For right now, it's more again just building the, can I follow a pattern, can I follow the formula, and can I simplify things appropriately, and then just kind of again take hold of the fact that like in the future there'll be a time where this actually makes sense why we would care to do that. And I promise it does have an application that makes things a lot easier for that moment when it presents itself. But anyway, that this point has worked through every example I wanted to for at least an introduction into the concepts we're doing. As always, though, if you have questions, this just maybe work through a few more examples in class and give me chances to help as needed. But yeah, anyway, as I always say at the end here, I appreciate you taking the time watching the video if you have, and we'll catch you next time.